All right. Hello, everyone, and welcome to our first video. Um, so this is just meant to be a short introduction to some of the topics that show up on Worksheet 1, and we'll go through them somewhat quickly to not take up too much time. Um, so uh, if we look at Worksheet 1, there's some algebra review, some fraction stuff. So I'll start there. And the basics, we need to know how to add, multiply, divide, subtract fractions. So here's just a short example. The way that I like to do it, if I'm adding fractions, as in example number 1, is to get a common denominator. 5 and 7 have a common multiple of 35. So if we just multiply the second fraction on the top and bottom by 5, and the first fraction by 7, then we get 21 over 35 plus 30 over 35. And then if we add these two together, when we add two fractions, the denominator stays the same, and the numerator, we just add the numerators, so we would get 51. We could try to simplify this to see if 51 simplifies. 51, I believe, is divisible by 3. Three goes into 5 one times 3 is 3. We subtract. 3 goes into 21 7 times. So 3 times 17 is 51. And so since 3 times 17 is 51 and 35 is just 5 times 7, this will not reduce at all. So this is our answer. Okay, we can leave it as an improper fraction rather than writing it as a mixed number. Okay, so I'm sure you've seen that before. How do we multiply fractions? This is a little bit different than addition. This one is actually easier, I think. We just multiply straight across. Multiply the numerators together, multiply the denominators together, and you arrive at your answer. So 3 times 6 is 18. 5 times 7 is 35. And then we check to see if we can reduce this. There are no common factors between 18 and 35. And so that's our answer. Division of fractions. We take our first fraction, 3/5, and then we multiply by the reciprocal of the second fraction. So we were dividing by 6/7. That means we need to multiply by 7/6. Okay, so then we multiply across and we get, well, now the division problem has become multiplication by the reciprocal. So I can multiply just the numerators to get 21, multiply denominators to get 30. In this case, it does look like there is, oh wait, is there a common factor? Yeah, 3, right? If you look at 21, that's 3 times 7, and 30 is 3 times 10, and so that 3 cancels out, and so we get 7 over 10. And that is our answer. Okay, so just a little bit of review there. I'm pretty sure you've all seen that before. So let's continue. Reminding ourselves what algebraic expressions are. An expression is basically just some statement, some mathematical statement that does not have an equals sign. Now that's one way to put it, I guess. It doesn't compare two quantities. So a couple expressions here are like this one, 4. That's just, we're expressing something, the number 4, a quantity of 4. Or 4x, if you think about what 4x means, it just means 4 times some number. And that number could be 2. 4 times 2 is 8. Or this is just 4 times a number. And then we can get more complicated expressions, 4x plus 8. This expression, 4x plus 8, has 2 terms, right? We would call these terms, 1 term, 2 terms. And, there's only 1 term in 4x because they are being multiplied together. Increasing just the complexity a little bit. 4x plus 2 is another expression. It also has 1 term. Because all of this is multiplied together, oops, wrong tool there. it's all kind of linked through multiplication. So we would say this is an expression. It doesn't have an equal sign and it's not comparing anything. When I say it's not comparing anything, I also mean it doesn't have a less than sign, a greater than sign, any of those other inequality signs. Now this one here, we can actually we can simplify the expression by distributing the 4. And, we'll see why we might want to do this later. If we multiply the 4, now we have an equivalent expression, but it has 2 terms, 4x and 8. Okay. All right. And then one of the more complicated expressions here on this page is this quadratic here. All right. So how do we simplify expressions? I believe there are some problems on our worksheet where we need to simplify some expressions. Yeah, problem number 5. And so one common way is, just look at what needs to be done. And it looks like here on this expression, there's a -1 here. And so since -1 is next to parentheses, that means we should distribute. It implies multiplication. So we can distribute that -1. And that gives us -3b -5 -7. And then if we combine like terms, there are 2 like terms here. So we have -3b -12. And that's as much as I can simplify this expression. -3b and -12 are not like terms since they don't have the same variables. One has a variable, one doesn't. Okay, so we can stop there. So that will be a common thing whenever you see multiplication. That's how you can simplify that part of the expression. So we can simplify this next one by also distributing. And we want to apply the order of operations. Maybe somebody might be thinking, just in case you're thinking, hey, why don't I, add this 7 with this -7? Why don't I combine those? Well, if you remember the order of operations, PEMDAS, or please excuse my dear Aunt Sally, there is multiplication here that needs to be done before you can do that addition. The addition that I mentioned of the -7 and the +7. So since multiplication takes precedence, we'll do the multiplication first. So we have 2y plus 14 plus 3y minus 7. We'll combine any like terms. Like terms are 2y and 3y. That gives us 5y if we combine those. And then a +14 and a -7 gives us +7. Okay. All right. Hopefully I'm not going too fast. I know a lot of the stuff you may have seen in the past. All right. Next. Let's look at linear equations. There are linear equations like in problem number 6 or problem number 7. And we want to look at the types of solutions that could result from a linear equation. Okay, so an equation now is just 2 expressions joined by an equal sign. Okay, so we have an expression on the left-hand side, an expression on the right-hand side, 18 minus x, and there's an equal sign between them. And so we want to see if we can find any values of x that will make this equation true. And the way that we could do that is by simplifying each expression on each side. So on the left-hand side, we could distribute. So this gives us 4x plus 3x minus 6. On the right-hand side, there isn't really anything to do to simplify, so we'll just leave that the same. Again, on the left-hand side, I can combine the 3x and 4x. And now we've simplified both expressions as much as they can on each side. And so what we can do now is move all the variable terms to the left-hand side. I can do that by adding x to the right-hand side I would have to add x to the left-hand side as well, and that would give me 8x. And then the -6, since I moved all the variable terms to the left, I'm going to move all the non-variable terms to the right-hand side. I'll do that by adding 6 to both sides to cancel out this -6. And if I add 6 to both sides, I get, what's 18 plus 6? That is 24. So I move the terms around a little bit. And then finally, here I have 8 times x. To eliminate that x and isolate the, I'm sorry, to eliminate the 8 and isolate the x, I can divide both sides by 8. So x is equal to 3. Okay. So x equals 3 would be the number that if I plugged into this equation, I would get a true statement. And yeah, let me take just a moment to talk about that. I'll write it in black up above. And so if I put, I'll do it down below. If I take my original equation for x plus 3 times x minus 2 equals 18 minus x, what could x be? Well, we've solved and we've determined that x is equal to 3. That means if we were to replace every x by a 3, we should get a true statement. So this is 12 plus 3 times, inside the parentheses, 3 minus 2 is 1, 18 minus 3 is 15, and 12 plus 3 is 15. Notice that this statement is true. That means that x equals 3 is my solution. And we would say that this equation has one solution. Now, what other kinds of solution sets might we get? Well, let's take a look at the next example. Um, 2a plus 4a minus 4. So we just distributed there. I'll distribute on this side as well. 1 plus 6a plus 3. If I combine like terms, I get 6a minus 4 equals 6a plus 4. And so again, I've simplified each expression on each side. Now I want to get all the variable terms on the left-hand side. Let me do that first. Minus 6a to get rid of that. And if I minus 6a on the other side, notice, minus 6a, they cancel out on the right side, minus 6a, they cancel out on the left side as well. And what we end up getting is -4 equals +4. And that is not true. -4 is not the same as +4. This is just a false statement. What this means is, since the variables canceled and we got a false statement, this means that there is no solution. There is no value for the variable that you could plug in to make it true. Okay, and you can try plugging in, a equals whatever you want, 0, a equals 1, a equals 3. There is no value of a that will make that will produce a true statement. This statement is always false. This is sometimes called a contradiction. If you read the textbook, that's what they call it there. Okay. Next, let's take a look at our last equation here. Distribute, and we get 2x plus 6 equals 4x plus 7. 4x plus 28. Hopefully I don't make any mistakes in these videos since there's nobody here to correct me. But you can tell me in class if you see a mistake. So 2x plus 6 is equal to is equal to 2x plus 28. And this is not how I intended this problem to work out, but that's okay. There's no mistake. We subtract 2x on both sides. The 2x's cancel. And we would get 6 equals 28. So what does this mean? The variables all canceled out, and we get a false statement. That also means that there is no solution. Okay. So 2 examples of no solution. Let's take a look at one more. I think I meant this to be slightly different. So let's see if I can change this just a little bit. Let's do one more example. So I'll make it very similar. 2 times x plus 3 equals 4x plus 7 minus 2x. And then let's put plus, let's take a plus 22 over here on the end, on the left-hand side. Now we're just forcing it to come out to how we want, but you'll see equations like this, in the worksheet that will have this result. So if we distribute, slight mistake here, the parentheses should be right there. So we get 22 plus 2x plus 6 is equal to 4x plus 28 minus 2x. And so when we simplify both sides, I can add the 22 and the 6, and so that gives me 22x plus 28. On the right-hand side, the 4x, if I take away 2x, that gives me 2x plus 28. And you can see that the left-hand side and the right-hand side are identical. So this time, if we subtract 2x on both sides, the variables still cancel each other out. But instead of getting a false statement, you get 28 equals 28. That's just true. So this implies that there are infinitely many solutions. Not only that, actually, all real numbers are solutions. And just as an example, let's go ahead and take this original equation here, and let's plug in a random number. Somewhat random, I guess I'll choose like 2. But you could plug in 3, or you could plug in 4, or 7, or 1.5, whatever you like, and it will come out to a true statement when you plug that number in, because we've just shown algebraically that these two expressions are equivalent on the left-hand side and the right-hand side. Okay, so 2 times, what did I say I was going to plug in? Let's do 3, and let's switch it up a little bit. Rather than 2. The number, as long as it's consistent across for all the x's, it will give me a true statement. 3 plus 7 minus 2 times 3. And let me just move this over so I'm not so close. Okay, so using the order of operations, I'll do whatever's in the parentheses first. 3 plus 3, 3 plus 7. And I'll do a little bit of multiplication here at the same time. 2 times 3 is 6. So this is 22 plus 12 equals 40 minus 6. 22 plus 12 is what? 34. And 40 minus 6 is 34. Notice this came out true. That shouldn't be a surprise, because when we tried to solve this algebraically, we got a statement that is always true. 28 is always equal to 28. And that implies that any value you plug in for x in this equation will be a solution. It will produce a true statement. All right. Almost done. We've got 3 topics left, and then we'll stop. Okay, so reducing fractions with or without variables. So reducing fractions, yeah, I think everybody, fractions generally people don't like them. But what's one way to do this? You can just, factor, look at the factorization, and if there's anything common in the numerator and denominator, you can cancel out, and we get 2/5. Now, sometimes you don't really want to write out a complete factorization, so you can just kind of, ask yourself, well, what do I know that 4 and 10 have in common? What factor do those two have in common? I like to write a little note like this, division by 2 on both top and bottom, and then that's 2/5. Now that comes in more handy when, you're working with something like example number 2, 12/60. I don't really want to write out the factorization for 60. It's, a little longer. So, but actually I just know that 12 goes into 60 5 times, right? If you think of the clock has 12 5-minute sections for an hour. So, I know that I can just divide both the top and bottom by 12, and I would arrive at my answer. 1/5. And even if you didn't know that both of these were divisible by 12, you could probably, see that both of them are divisible by 6. So 12 divided by 6 is 2, and 60 divided by 6 is 10. And then I say, hey, wait, these are both divisible by 2 now. And so I still arrive at 1/5. Okay. So now throwing variables in the mix here. Variables, essentially, we already talked about how to reduce numbers, so I'll just leave those as 4/32. The variables x to the 3rd power just means x times x times x, and x to the 5th power means, a product of 5 x's. So it's a similar idea, and we want to just be able to kind of see it in our head. We'd say these 3 x's and these 3 x's are common on the numerator and denominator, so I can cross those out. 4 and 32 are both divisible by 4, so I can reduce that. And it looks like it reduces to 1/8x squared. There are 2 x's left in the denominator. Exponent rules is our second to the last topic. There are various exponent rules. You can look them up in the textbook or just Google exponent rules, and you'll get a list of like 7 rules. Here are some of them. And the first one is when you're multiplying 2 quantities that have like bases. So they have to have the same base, x to the 4th and x to the 12th. That's what we have here in example number 1. How do we multiply 2 exponential expressions with the same base? The base stays the same, and we add the exponents. So this is x to the 16. I write the intermediate step. It's not really necessary to do that. How do we divide 2 expressions, as in example number 2? We would leave the base the same and subtract the exponents. Top exponent minus bottom exponent. 3 minus 5. And so that gives us x to the -2. And as we're going to see, actually below in just a moment, that a negative exponent can be written as a reciprocal. So x to the -2 can be written as 1/x to the 2. And we can leave our answer that way. A lot of times it's good practice to write negative exponents as positive exponents by taking the reciprocal. And then what about this cube root of x? There is a rule, this rule here, that allows us to write a cube root, an nth root, as an exponent. And essentially, this number here, the one that's right there, the index, becomes the denominator of the exponent. And then the number that we're raising the base to becomes the numerator of that exponent. So this expression, the cube root of x, can be written as x to the 1/3. And we can leave that there. Okay, hopefully you can't hear my kids outside. And the last problem here for exponent rules is the one with the negative. Oh, we just did this one. X to the -2. That's okay though, because it's helpful. X to the -2 can be written as 1 over x to the 2, as we said. And sometimes it seems like, well, why would we just, that what is that useful for? Well, if we have a number like 4 to the -2, maybe it's a little bit more useful, or seems a little bit more useful, because 4 to the -2 can be written as 1 over 4 to the 2, and then we can actually do something with that. We can square the 4, 1 over 16. I'm not trying to say that this is not useful. It will be useful as we get deeper and deeper into these topics. We will need to rewrite expressions sometimes and work with them in different forms. Okay, very good. The last topic here is solving word problems. And, this is similar to problem number 9. And essentially what we want to do is we want to just try to read the problem, maybe write down what you think the variable is, and then try to make an equation that represents the situation. So I pulled up a problem here from the textbook, and I'll write it down, and then we can go through it. Well, let me read the problem. Hopefully you can see it there as well. It says, and this is problem number 70 in the textbook. It says, when the smaller of two consecutive integers is added to 3 times the larger, the result is 51. Find the smallest integer. Okay, so here we're talking about 2 consecutive integers. So 1 and 2 are consecutive integers. 17 and 18 are consecutive integers. And let's say 23 and 24 are consecutive integers. Just one number that follows another. So how can we write these in general? Notice that, to get to the next consecutive integer, we need to add 1 each time. So if we want to represent them more generally, we could say x is the first of the consecutive integers, and then the next one is going to be x plus 1 more. So x and x plus 1 can represent 2 consecutive integers as long as, x is an integer. Okay, so which one is the smaller of these integers? X, and then x plus 1 is the larger. So let me write down a little bit of, a few words here. So the smaller integer is x, the larger is x plus 1. We don't have to use a second variable like y or something like that. We can just use x plus 1. And then, okay, let's see. When the smaller of 2 consecutive integers, so here's the smaller, is added to 3 times the larger, the result is 51. Okay, so the smaller is added to 3 times the larger. The result is 51. Okay, so kind of breaking down how we set that equation up. I know it's a lot easier to see somebody do it than it is to do it yourself. So, you'll have other problems here. This one's not too bad. Problem A, let's just read it real quick. It says, a desk and a chair cost $51 together. The chair cost $12 less than the desk. How much did the desk cost? So, you can set up a variable for the desk. You can set up a variable for the chair if you'd like, and set up equations to be able to solve this problem. Okay, so let's go ahead and solve this one here. I'll just distribute the 3. This is 3x plus 3 equals 51. So 4x plus 3 equals 51. If I subtract 3 on both sides, then 4x equals 48. And dividing by 4 on both sides, I get x equals 48 divided by 4 is 12. And so I'm saying x is 12. If I go back to how I define these variables, the smaller integer is 12. The larger one is x plus 1. So that would be 12 plus 1, which, 13 is the next consecutive integer. So 12 and 13 are the integers. Now, they are consecutive. Let's just check our answer here. What did the statement say again? It said when the smaller of 2 consecutive integers is added to 3 times the larger, the result is, and let's see here, let me actually add this up. 3 times 13 is 39. 12. If I add 12, I get 51. And notice if I had, the result is 51. Notice that, plugging in my answer results in a true statement, which implies that, the answers I got are correct. Okay, how long was that? 30 minutes. I'll stop there. And there are a couple more, maybe another topic that I could go over. But I will wait until next time to do that. And the last topic I think that I could go over is solving a system of equations. And this video is already long enough, so I'll put that in the next video. All right, so don't forget to put a like on the video or leave a comment. Let me know what you like, what you don't like. And hopefully it came out all right.